Welcome to this Top 10 deep dive into one of the most profound scientific achievements of the human mind, the theory of general relativity. In this journey, we will count down from number 10 to number 1, exploring how Albert Einstein reshaped our understanding of gravity, space, and time. This theory is more than equations and symbols. It is the story of how reality itself bends, twists and evolves in ways that challenge our everyday intuition. Get ready to explore the universe in a way you may never have imagined. Number 10. General relativity shows us the deep connection between matter, energy, space, and time. It teaches us that reality is not fixed and absolute, but flexible and dynamic, our everyday sense of space and time. As rigid and unchanging is actually an illusion. Instead, space and time can stretch, bend, and ripple under the influence of energy and mass. This revolutionary idea has reshaped physics, philosophy, and the way we view our place in the cosmos. After more than a century, general relativity continues to pass experimental tests with flying colors. It stands as one of the greatest intellectual achievements in human history. Number 9. General relativity also tells us about the structure and fate of the universe itself. When Einstein applied his equations to the entire cosmos, he discovered that space-time could expand or contract. Later, astronomers confirmed that the universe is expanding, and this gave rise to the Big Bang theory. Even more astonishing, modern measurements show that the expansion of the universe is accelerating, driven by a mysterious effect called dark energy. While general relativity does not tell us exactly what dark energy is, it provides the framework within which we study and measure these cosmic mysteries. Without this theory, we would not even know how to describe the evolution of the universe. Number 8. Another groundbreaking prediction of general relativity is gravitational waves. These are ripples in the fabric of spacetime created by the acceleration of massive objects such as black holes or neutron stars colliding. Imagine two black holes spiraling into each other, releasing energy so immense that it disturbs the universe itself, like ripples spreading across a pond. General relativity predicted this phenomenon a century before technology caught up. In 2015, the LIGO experiment directly detected gravitational waves, for the first time proving Einstein's vision correct. This discovery gave birth to gravitational wave astronomy, a whole new way of observing violent cosmic events billions of light years away. Number 7. One of the most dramatic consequences of general relativity is the existence of black holes. These cosmic monsters form when massive stars collapse under their own gravity to such an extent that space-time curves infinitely. The escape velocity exceeds the speed of light, which means nothing can escape beyond the event horizon, the invisible boundary surrounding the black hole. Once thought to be only mathematical oddities, black holes are now known to be real observations. Show stars orbiting invisible massive objects, and in 2019, the Event Horizon telescope captured the first image of a black hole shadow. Black holes are no longer science fiction. They are real laboratories of extreme physics. Number 6. General relativity also revealed that time itself is not absolute, but relative time runs differently depending on speed and gravity. This phenomenon is called time dilation. A clock near a massive object ticks more slowly than a clock farther away. For example, clocks on Earth run slightly slower than clocks on satellites orbiting above us. The difference is tiny but measurable and crucial. The Global Positioning System, or GPS, uses signals from satellites and relies on extreme precision. Without correcting for relativistic effects, GPS would produce errors of several kilometers per day. This shows that the strange predictions of relativity directly affect our everyday lives. Number 5. Another striking prediction of general relativity is gravitational lensing. Light itself follows the curvature of space-time. When light passes near a massive object, its path bends. Just like matter, this bending creates beautiful effects in astronomy. For example, distant galaxies appear distorted, magnified, or duplicated because their light curves around closer massive objects. This effect was confirmed during a solar eclipse in 1919, when starlight was seen bending around the sun. That experiment instantly catapulted Einstein to worldwide fame and confirmed that his strange new vision of gravity was correct. Gravitational lensing is now used regularly to map galaxies and detect hidden matter. Number 4. General relativity also solved mysteries that Newtonian physics could not explain. One important case is the orbit of Mercury. The tiny planet closest to the Sun has an orbit that shifts slightly with each revolution. Newton's equations could not account for this discrepancy, but general relativity did. The intense curvature of space-time near the Sun explained Mercury's orbit perfectly. This success was one of the early triumphs of Einstein's work and gave strong support to the theory when it was still new and controversial. Number 3. The theory also explains how massive objects like the Sun curve the very fabric of space-time. Imagine space-time as a stretched rubber sheet. A heavy ball placed on it makes a dip, and smaller balls roll toward the dip, not because they are pulled by a force, but because the surface itself is curved. Likewise, planets orbit the Sun because the Sun curves the surrounding space, time, and the planets follow natural curved paths called geodesics. This visualization helps us see why gravity is not a mysterious force, but the geometry of the universe itself. Number 2. To fully grasp general relativity, we must understand that space and time are not separate. They are woven together into one four-dimensional fabric called space-time. Events are described by both where and when they occur. Matter and energy are not passive inhabitants of this stage. Instead, they actively shape it. They tell space-time how to curve, and in return, the curvature tells matter and light how to move. This principle is the heart of general relativity and sets it apart from all previous ideas. About gravity. Number 1. At its foundation, the theory of general relativity was introduced by Albert Einstein in the early 20th century. It replaced the Newtonian idea of gravity as a force acting at a distance. Einstein realized that gravity was not a force, but the effect of curved space-time. This radical new understanding changed physics forever. It explained phenomena Newton's laws could not, and it opened the door to discoveries about black holes, gravitational waves, and the expansion of the universe. General relativity is not just a theory of gravity. It is a new way of seeing reality itself. You have just traveled through the top 10 key ideas of the theory of general relativity from its PHS. with broad philosophical meaning to its practical applications and cosmic predictions. This theory shows us that the universe is stranger, more dynamic, and more beautiful than common sense alone could ever reveal. From the ticking of covelites to the dance of black holes, relativity shapes the world we live in and the universe we observe. And more than 100 years after Einstein first published it, general relativity remains a shining example of human curiosity, imagination, and the power of science to transform our view of reality.